Somewhere in your body, right now, an electron is orbiting a carbon atom in a strand of your DNA. 400 light years away, inside a dying star, another electron is being crushed into a state of matter so dense that a single teaspoon would weigh more than a mountain. These two particles have never met. They exist in conditions separated by unimaginable extremes of temperature, pressure, and time. And yet, if you could somehow swap them, nothing in the universe would change. Not one experiment, not one measurement, not one law of physics would be able to tell the difference. They are not similar, they are not nearly identical. They are, in the strictest sense that physics allows, exactly the same particle, indistinguishable in every conceivable way. This is one of those facts that sounds almost too simple to be strange, until you actually sit with it. Every electron in the observable universe has precisely the same mass, precisely the same charge, precisely the same intrinsic spin. Not approximately, not to several decimal places. Exactly. There is no factory stamping these things out with a slight margin of error. There is no cosmic quality control process weeding out defective units. As far as every experiment ever conducted can tell, there is no such thing as a slightly different electron, and there never has been. For most of the history of science, sameness like this simply did not exist in nature. Look at any two grains of sand, any two leaves on a tree, any two stars in the sky, and you will find differences, however microscopic. Even objects manufactured to the tightest tolerances by human machines carry some imperfection at the atomic level. Nature, as far as we can tell from the macroscopic world, abhors true identity. So when physicists in the early 20th century began to suspect that subatomic particles might be perfectly, unconditionally identical to one another, the claim did not sit comfortably. It took a strange combination of theoretical necessity, experimental confirmation, and decades of stress testing before scientists were willing to accept it. And even now, in laboratories around the world, researchers are still hunting for any tiny crack in that claim, because if they ever found one, it would rewrite physics from the ground up. This is the story of how we came to believe that every electron in the universe is the same particle, why the evidence for that belief is stronger than almost any other claim in science, and why some of the smartest people who ever lived have argued that the reason might be even stranger than the fact itself. Before we get to the physics, it helps to understand just how radical this claim actually is when placed against everyday experience. Human beings are pattern recognition machines, and one of the deepest patterns we rely on is the assumption that every object has its own individual identity, its own continuous history, its own hidden thread connecting past to present. Twins may look alike, but a mother can tell them apart. Manufactured parts may appear identical on an assembly line, but under a strong enough microscope, scratches, impurities, and irregularities always emerge. This assumption is so deeply built into how we think that early quantum physicists initially resisted the idea that nature could work any other way. Surely, they thought, if we simply looked closely enough, some distinguishing feature would eventually appear. Some tiny asymmetry, some individual fingerprint, some way of tagging one electron as different from its neighbor. What emerged instead, through a combination of theoretical insight and experimental confirmation, was something far stranger than mere similarity. It was total, structural, mathematically enforced sameness, with no exceptions found in nearly a century of searching. The story begins in the 1920s, in the middle of the chaotic and thrilling birth of quantum mechanics. Physicists were trying to understand why atoms behave the way they do. Why do electrons in an atom arrange themselves into distinct shells, instead of all collapsing down to the lowest possible energy level, sitting right on top of the nucleus? If electrons were simply tiny charged balls obeying classical physics, there would be no reason for them to spread out into shells at all. They should all fall to the same lowest energy orbit, like water flowing to the bottom of a container. But that is not what happens, and the reason is one of the strangest rules in all of physics. In 1925, a young Austrian physicist named Wolfgang Pauli proposed a rule that would later carry his name. Pauli's exclusion principle states that no two electrons in an atom can occupy the same quantum state at the same time. If one electron in an atom has a particular set of quantum numbers describing its energy, its orbital shape, and its spin, no other electron in that atom is allowed to have that exact same combination. This single rule explains why atoms build up in layered shells, why the periodic table has the structure it does, and ultimately why chemistry works the way it does at all. Without the Pauli exclusion principle, there would be no distinction between hydrogen and helium beyond nuclear charge. There would be no complex chemistry, no stable solid matter, and almost certainly no life. What made Pauli's proposal so unusual at the time was that he arrived at it before anyone fully understood why it should be true. He noticed the pattern in atomic spectra, the way electron shells filled up in a strict, orderly sequence, and he worked backward to a rule that fit the data, even before the deeper reason for that rule was understood. It was only with the later development of the mathematics of quantum spin and the recognition that electrons carry an intrinsic angular momentum that can only take on two possible orientations that the full picture came into focus. Pauli himself received the Nobel Prize in Physics in 1945 for this discovery, decades after he first proposed it, a reflection of how long it took the physics community to fully absorb its implications. For a rule this fundamental to matter, it is worth remembering that it started as an empirical pattern noticed in the fine details of light emitted by excited atoms, long before anyone could explain the deeper reason behind it. But here is the deeper and stranger implication buried inside Pauli's rule, one that took physicists years to fully digest. For the exclusion principle to work as an absolute law rather than a strange coincidence, electrons could not simply be similar particles that happen to repel each other from occupying the same state. They had to be fundamentally, philosophically identical. Not just identical in the sense of sharing the same properties, the way two perfectly manufactured ball bearings might share the same weight and diameter. They had to be identical in a deeper sense, interchangeable in a way that no classical object can be. To understand why this distinction matters, imagine you have two identical-looking coins in your pocket. Even if they were struck from the same mold on the same assembly line, they are still in principle distinguishable. You could, in theory, track coin number 1 and coin number 2 separately, follow their individual histories, tell which one has been in your pocket longer. Classical identity always leaves room for a hidden label, even if that label is impossible to read in practice. Quantum identity does not work this way. When physicists say that two electrons are indistinguishable, they mean there is no hidden label at all, even in principle. If you take two electrons, swap their positions, and then look at the system again, there is no experiment in the physical universe that could tell you whether a swap occurred. This is not simply a statement about the limits of our measuring instruments. It is a statement about the fundamental structure of reality itself. In classical physics, even a hidden, unmeasurable label would still, in principle, exist. Quantum mechanics removes even that possibility. The particles do not merely look the same. There is no fact of the matter about which one is which, because the underlying description of the system treats them as fundamentally interchangeable entities from the very beginning. The mathematics of quantum mechanics builds this indistinguishability directly into the wave function describing the particles, through what is known as the symmetrization postulate. For particles like electrons, called fermions, swapping any two of them causes the overall quantum wave function to flip sign. This antisymmetry is not a minor mathematical detail. It is the direct cause of the Pauli exclusion principle. If two electrons ever did occupy the exact same state, swapping them would leave the wave function completely unchanged, which contradicts the required antisymmetry, forcing the probability of that state to be exactly zero. In other words, the reason electrons refuse to pile into the same energy level is not because they are repelling each other in some ordinary physical sense. It is because the universe's mathematical bookkeeping makes that configuration impossible. This connection between the spin of a particle and its statistical behavior was formalized in what physicists now call the spin statistics theorem, work developed through the contributions of Wolfgang Pauli and later placed on a rigorous theoretical foundation within the framework of relativistic quantum field theory. The theorem shows that particles with half-integer spin, like electrons, must be fermions obeying this exclusion behavior, while particles with integer spin, like photons, are bosons that happily pile into the same state together. This is why laser light can consist of countless photons all behaving in perfect lockstep, while matter made of electrons, protons and neutrons must spread out and take up space. The solidity of the chair you are sitting on, the fact that your hand does not pass through a table, the entire structure of atoms and molecules, all of it traces back to this deep rule about the identical, interchangeable nature of fermions. By the middle of the 20th century, quantum field theory offered an explanation that went even further. And this is where the story takes its strangest turn. In quantum field theory, particles are not thought of as tiny individual objects traveling through space, the way you might picture a marble rolling across a table. Instead, physicists describe the universe as filled with fields, continuous quantities that exist at every point in space. There is an electron field permeating the entire universe. What we call an individual electron is simply a localized excitation, a ripple or a quantized disturbance in that underlying field. This is the same basic framework used to describe the electromagnetic field, where a photon is a quantized ripple in the electromagnetic field itself. If this picture is correct, then it immediately explains why every electron is identical. They are not separate objects that happen to share the same properties. They are all excitations of the exact same underlying field, in the same way that every ripple on the surface of a pond is made of the same water. You would never ask why one ripple on a pond is identical to another ripple on the same pond in terms of what it is made of, because they are both simply patterns in the same medium. Quantum field theory suggests something similar is happening with electrons. There are not billions of trillions of distinct electron objects scattered throughout the universe. There is one electron field, and what we perceive as individual electrons are simply excitations of that single universal structure. This idea connects to one of the most famous stories in the history of modern physics, a story that begins with a phone call. In the late 1940s, the physicist Richard Feynman, who would go on to help develop quantum electrodynamics and win the Nobel Prize in Physics, described a conversation he once had with his doctoral advisor, John Archibald Wheeler. Wheeler, known for his vivid imagination and his gift for asking audacious questions, proposed to Feynman an idea that sounds almost like something from science fiction. What if there's only a single electron in the entire universe? What if every electron we ever observe and every positron, its positively charged antimatter counterpart, is actually the same one electron, tracing an impossibly complicated path that weaves forward and backward through time? In this picture, when the electron moves forward through time, we observe it as an ordinary electron. When it moves backward through time, we observe it as a positron. A single particle, zigzagging endlessly through the fourth dimension, could in principle create the appearance of countless electrons and positrons scattered throughout space and across cosmic history, simply because its world line crosses any given moment in time many times over. By Feynman's own account, the phone call came late one night, and Wheeler opened with a line that has since become famous in physics folklore. He told Feynman he knew why all electrons have the same charge and the same mass, and the reason was that they were all the same electron. It is easy to imagine the young Feynman's reaction, somewhere between amusement and disbelief, at receiving a phone call built around a claim this audacious. Yet rather than dismiss it outright, Feynman worked through the mathematics of what such a picture would imply, and in doing so stumbled onto a genuinely useful piece of formalism: the idea that a positron could be treated, mathematically, as an electron whose time coordinate runs backward. This trick simplified the bookkeeping of particle interactions so elegantly that it became a permanent part of the Feynman diagram technique still taught to physics students today. Wheeler offered this idea partly as a playful thought experiment, a way of explaining why every electron is identical to every other electron. If they are all in some deep sense the same particle, then their sameness stops being a mysterious coincidence and becomes almost a logical necessity. Feynman took the idea seriously enough to explore its mathematical consequences, and it directly inspired his development of the concept that positrons can be treated mathematically as electrons moving backward in time within the Feynman diagram formalism, a technique still used throughout particle physics today. But Feynman himself, in later retellings of the story, pointed out the idea's most obvious problem. If there truly were only one electron zigzagging through all of time, then the number of electrons in the universe at any given moment should roughly equal the number of positrons, since the particle would need to cross forward and backward roughly equally often. But observationally, our universe contains vastly more electrons than positrons. Positrons are rare, produced only in specific high-energy processes, and quickly annihilated. Feynman recalled Wheeler suggesting that perhaps the missing positrons were hidden inside protons, an idea that never held up since we now understand protons are built from quarks, not positrons in disguise. So the single electron hypothesis, in its literal form, does not match our universe. But the idea it was trying to explain has not gone away. It has simply been absorbed into the modern language of quantum field theory. Physicists no longer need to imagine one particle zigzagging through time to explain why electrons are identical. The field itself does that work. Every excitation of the electron field inherits the exact same fundamental properties, because those properties are not attributes of an individual object, but structural features of the field equation that governs the entire universe. The mass of the electron, its charge, its spin, are not measurements of some individual particle's personal characteristics. They are parameters written into the fundamental equations describing reality itself. The same way the speed of a wave on a guitar string depends on the tension and mass of that specific string. not on which particular moment in time the wave happens to be traveling through it. This is where the investigation has to slow down and ask an uncomfortable question, because a good case file does not simply accept the tiniest explanation and move on. It is worth pausing here for a reality check, because it would be easy to walk away from this story believing that physicists have simply proven with total certainty that electrons are identical because they share a single field. That is not quite accurate, and the distinction matters. Quantum field theory is an extraordinarily successful framework, one of the most rigorously tested theories in the history of science. But the claim that electrons are perfectly identical is not something physicists accepted purely on theoretical elegance. It is an empirical claim, and empirical claims require empirical proof. So what is the actual evidence, distinct from the theoretical framework, that every electron truly is the same as every other? The strongest direct evidence comes from an area of physics known as precision metrology, the science of extremely careful measurement. One of the most precisely measured quantities in all of science is something called the electron's magnetic moment, often expressed through a number called the G factor, which describes how the electron behaves as a tiny magnet in response to a magnetic field. Quantum electrodynamics predicts the value of this G factor to an extraordinary number of decimal places. And experimental physicists, including the team led by Gerald Gabrielse at Harvard University, have measured the electron's magnetic moment to a precision of roughly 1 part in a trillion. What makes this measurement so relevant to our investigation is not just its precision, but what it implies. These measurements have been performed on electrons captured from wildly different sources, produced in different laboratories, at different times, using different apparatus. If electrons varied even slightly from one to another, these measurements would show scatter, inconsistency, tiny discrepancies between one electron trapped in one experiment and another electron trapped somewhere else. Instead, every measurement of the electron's fundamental properties agrees to the limits of our best instruments, regardless of where or when that electron was produced. This is not a proof in the mathematical sense, since science does not deal in absolute proofs. But it is about as close to overwhelming evidence as experimental physics can offer. If electrons carried even a hidden, undetectable individuality, some trace of it would be expected to show up eventually across the sheer volume of experiments performed over the past century. None has. It is worth appreciating just how demanding this kind of measurement really is. Gabrielse's technique involves isolating a single electron inside an extremely cold electromagnetic trap, sometimes for months at a time, and observing its quantum behavior with such precision that even tiny theoretical corrections predicted by quantum electrodynamics, effects arising from an electron's brief interactions with virtual particles popping in and out of existence around it, must be accounted for to match the data. The agreement between this experimental value and the theoretical prediction is often cited as one of the most successful quantitative agreements between theory and experiment in the history of science. And crucially, this same level of agreement holds regardless of which electron is trapped, when it was captured, or where the experiment takes place. A physicist repeating this measurement in Tokyo, Boston, or Geneva would, within experimental uncertainty, get the same number every time. There is also indirect but powerful evidence built into the structure of ordinary matter itself. The entire predictive power of chemistry depends on electrons being identical, because if electrons varied even slightly from atom to atom, the periodic table would not have consistent, repeatable properties. Every atom of carbon would not behave the same way. Every hydrogen bond would not form with the same strength. Yet chemistry works with breathtaking reliability, precisely because electron behavior is uniform across every sample of every element ever tested, whether that sample originated in a laboratory on Earth or in light emitted from a star billions of light years away. When astronomers analyze the spectral lines of distant galaxies, they are reading the fingerprint of electron transitions inside atoms that formed under wildly different cosmic conditions, sometimes billions of years in the past. And those fingerprints match the same transitions measured in labs today. This is one of the most quietly astonishing facts in all of astrophysics. The laws governing electron behavior in a star 9 billion light-years away appear to be the same laws governing the electrons in the device you are using to watch this right now. None of this proves that a stranger explanation, like some deep symmetry we have not yet discovered, could not someday reveal subtle variations at scales we cannot currently probe. Science does not deal in final answers, but the honest, evidence-based conclusion is this. Every test physicists have devised, across nearly a century of increasingly precise experimentation, has failed to find any distinguishing feature between one electron and another. The identical nature of electrons is not a philosophical assumption layered on top of physics. It is one of the most rigorously tested empirical facts we possess. The consequences of this fact reach far beyond abstract theory, shaping the physical world in ways most people never think about. Consider what would happen if the Pauli exclusion principle and the underlying identical nature of electrons that makes it necessary simply stopped applying. Matter as we know it would be impossible. Every electron in every atom would collapse toward the lowest possible energy state, and the distinct chemical identities of different elements would disappear. The rich structure of the periodic table, the very possibility of complex molecules, and by extension the possibility of biology and life, all depend on the fact that electrons refuse to share the same quantum state. This is not a small technical footnote. It is one of the load-bearing pillars holding up the physical universe as we experience it. The exclusion principle also governs some of the most extreme objects in the cosmos. When a star like our Sun exhausts its nuclear fuel, it eventually collapses under its own gravity. In many cases, that collapse is halted not by any conventional pressure, but by something called electron degeneracy pressure, a direct consequence of the Pauli exclusion principle. As the star's core is compressed, its electrons are forced into ever smaller volumes of space, but the exclusion principle forbids them from occupying identical quantum states. This resistance, described mathematically by the physicist Subrahmanyan Chandrasekhar in the 1930s, creates an outward pressure powerful enough to support the crushing weight of a dying star, forming what we call a white dwarf. Chandrasekhar calculated that this resistance has a limit, now known as the Chandrasekhar limit, beyond which even electron degeneracy pressure cannot hold back gravitational collapse, leading instead to the formation of a neutron star, or, in more extreme cases, a black hole. Somewhere out there right now, there are stars held up entirely by the stubborn refusal of electrons to become identical in their quantum state to their neighbors. A refusal that only makes sense because those electrons are, in every other respect, absolutely identical to one another. Chandrasekhar developed this insight as a young researcher in the early 1930s, working out the mathematics during a long sea voyage from India to England. And his conclusion was initially met with skepticism from senior figures in the field, including the astronomer Arthur Eddington, who publicly doubted that nature would allow stars to collapse in the way Chandrasekhar's equations predicted. It took years and the accumulation of further observational and theoretical evidence before the scientific community came to accept that Chandrasekhar had been right all along. He would later share the Nobel Prize in Physics in 1983 for this work, a reminder that even correct, rigorously derived physics can face resistance before the evidence becomes undeniable. The pattern is a familiar one throughout this story. An idea about the deep structural sameness of electrons meets initial doubt and only settles into accepted fact once experiment and observation leave no other honest conclusion available. It is a strange kind of poetry once you sit with it. The same underlying fact, the perfect interchangeable sameness of electrons, is responsible both for the intricate chemistry that allows carbon-based life to exist and for the crushing physics that determines the ultimate fate of dying stars. A single rule about particle identity threads through biology, chemistry, and astrophysics all at once, connecting the electrons in your bloodstream to the electrons holding up the corpses of stars scattered across the galaxy. So where does the investigation stand today? Modern physics continues probing the identical nature of electrons from new angles, searching for any deviation that might hint at physics beyond the current standard model of particle physics. One active area of research involves searching for what is called the electron's electric dipole moment, a hypothetical property that, if detected, would indicate a tiny asymmetry in the electron's internal structure. So far, experiments looking for this property, including work conducted by research groups studying molecules like thorium monoxide, have found values consistent with zero, placing increasingly tight constraints on theories that predict physics beyond the standard model. Every null result, every failed attempt to find some hidden asymmetry or individuality in the electron, adds another layer of confidence to the picture we have built. The electron remains, as far as the evidence shows, a perfect, structureless, dimensionless point of charge and spin, with no internal architecture that could ever make one instance of it different from another. There is something worth sitting with in this conclusion, something that separates it from many of the mysteries explored in other investigations. Usually, when we uncover the reality behind a myth, we find nuance, complication, exceptions to the rule. Here, the deeper we dig, the simpler and more absolute the answer becomes. Every electron truly is the same. Not similar, not nearly identical, the same, in the most literal sense modern physics can express. Whether Wheeler and Feynman's playful idea of a single particle zigzagging through time turns out to hold any literal truth, or whether the real explanation lies entirely within the elegant mathematics of quantum fields, the underlying fact remains one of the most quietly radical discoveries in the history of science. Look at your own hand. Every electron inside every atom of every cell is, in the deepest sense physics can measure, identical to an electron sitting inside a star on the far side of the observable universe. Two objects separated by unimaginable distance and time, and yet fundamentally, provably, the same. The next time someone tells you that everything in the universe is unique, that no two things are ever truly alike, you will know of at least one exception, hiding in plain sight inside every atom around you, quietly holding up the entire structure of matter itself. It is a rare thing in science to find a claim this absolute that has survived a century of the most demanding scrutiny physics can offer, tested through atomic spectra, precision magnetic moment measurements, searches for electric dipole moments, and the extreme physics of collapsing stars, without a single confirmed exception ever turning up. If this kind of evidence-based investigation into the strange rules hiding inside ordinary reality is the kind of thing that keeps your curiosity sharp, there is more of it waiting, one case file at a time.